All right, let's do some more examples. This first one, hoping is a little more straightforward logic-wise, but the math might be trickier. And the second one is a little bit more complicated logic-wise, and we'll see about the math. All right, so here we're going to prove this other thing that we talked about earlier. And remember that the way to start these proofs is putting some kind of predicate around the natural numbers. So let's say, all right, let's say P of n is the proposition that this is true for x equals n. All right. And our base case is not going to be at 0 anymore. That would be a little silly from 1 to 0. Our base case is going to be 1. It's going to be really quite nice. Base case is going to be n equals 1 this time, because again, we want to start at the smallest one. The smallest thing that makes sense here is 1. So what do we have if n equals 1? Can we show p of 1? Well, let's start with one side and show it equals the other side. The sum from I equals 1 to 1 of I is very silly. That's just 1, right? What does this notation mean? This notation means you're adding up all the i's, starting from I is 1 and going till I is 1. So you're adding up all the i's in order, but there's only one of them, and its value is 1. All right. Now, again, we also, this is our left-hand side, right? What does our right-hand side look like? Well, the right-hand side, if x is 1, it's going to be 1 times 1 plus 1 over 2, right? Plugging in 1 into this, what does that simplify to? That simplifies to 2 over 2, which is 1. Oh, the left-hand side equals the right-hand side. Check, check. Right? So we've shown it for the base case. When x is just 1, yeah, this is true. That's easy to show. We just did. The sum of just going up to 1 is, yep, that formula holds. Now, of course, the induction step is more complicated. Let's give ourselves some room. Okay, so induction step is going to say, okay, does P of n imply P of n plus 1? This is what we want. We want to show this. So we're going to assume P of n. We're going to assume that if it's the case that the sum from 1 up to n of I is n times n plus 1 over 2, if that's the case, can we prove that the sum from I equals 1 to n plus 1 of I is true? How do we write that? Well, everywhere that there was an n, we're just now putting an n plus 1. So this n becomes an n plus 1. This n also becomes an n plus 1. And there's still that plus 1 from before. Okay. So this is what we want to show. Let's clean this up a little bit. All right, this is just n plus 2 now. This is what we want to show. Because if, right, this is showing the implication. If blue implies green, then we're done. So we'll say, if blue is true, can we show green? So now it's a little hard to figure out what side you want to start with. But I'm going to start with the left-hand side. If you're ever unsure, you can always choose one and see if it works. And then if that doesn't work, try the other one. So let's start with the left-hand side. Notice that the sum from I equals 1 to n plus 1 of I. What does this mean, right? This means we're adding up all the i's, starting from 1, and then 2, and then 3, and then 4, all the way up to n plus 1. What's the number before n plus 1? Is n. So a very common strategy when you're dealing with sums like this is let's break this up into two different sums. How do we know what sum we want to break it up into? We're going to want to use our induction hypothesis. We're going to want to use this blue part up here. okay, we're going to want to put it in terms of n. So the sum from 1 to n plus 1 is a sum from 1 to n, and then the n plus 1 part. So, right, you can think about it this way, right? The sum from 1 to n plus 1 is the sum from 1 to n plus the sum from n plus 1 to n plus 1. Right, just break it up into two different sums is fine because we can break up adding. So this is the sum, I equals 1 to n of I, which is really nice because we know what that equals, plus what happens when I is n plus 1. It's just n plus 1. When I is n plus 1, it's just n plus 1. Now this is really exciting because we know that this is equal to the blue thing. That's our induction hypothesis. We're assuming that's true. So that's n times n plus 1 over 2. And now, now we're kind of stuck. See how your algebra is. And again, algebra is not a big focus of this class, but we will need algebra for this problem. This is where we started. We started with the left-hand side. This is what we want. Can we make these two circled things equal to each other? Can we make what we just showed equal to the n plus 1, n plus 2 over 2? Well, let's try. What we have is not one fraction, but what we want is one fraction. So we're going to need to have everything as one fraction. So how can we combine fractions? Well, we combine fractions by getting a common denominator. So we're going to need to multiply this by 2 over 2. We're going to get n times n plus 1 over 2 plus, let's distribute that to 2n plus 2 over 2. And now we can combine the fractions. And we'll need to eventually combine like terms as well. So let's distribute out this first term. We're going to get n squared plus n. That's the part that came from the first part. Plus 2n plus 2. That's what came from the second fraction. Over 2. And even though I went to a same page, let's remember what we want this to be. We want this to be n plus 1, n plus 2 over 2. N plus 1, n plus 2 over 2. Whenever you're proving something like this, it's so useful to always keep in mind what you're trying to get to. Well, this is factored. This is not factored. Let's combine like terms and try to factor. All right. N squared plus 3n plus 2. Now, hopefully this factors to this. Let's just check. N squared plus 2n plus 1n is 3n plus 2. Great. It does factor like that. This is n plus 1, n plus 2 over 2, which is exactly what we wanted to show. This is the right-hand side. We started with the left-hand side of this green thing, what we wanted to show. We showed that it was equal to the right-hand side. We've done and completed the inductive step. Okay, so check. So we know it's true for the base case. We know that if it's true for any case, it's always true for the next case. So we have the tools to say, we know it's true for 1, which means it's true for 2, which means it's true for 3, which means it's true for 4, which means it's true for 5, and then 6, and then 7, and then 8, and then 9, and then 10. We've shown it's true for any natural number. Okay? So we know that by induction, we've shown that the sum from I equals 1 to n of n times n plus 1 over 2. I'm getting my variables mixed up. I times I plus 1. Oh my gosh, it's just I. Is equal to n times n plus 1 over 2. I should have just went to the back page and copied it. But that's how we prove it. Again, if this is enough examples, you don't need to keep watching. Right? If you're feeling good about this process, you don't need to keep watching. But if you want to see more examples of what weak form induction can look like, I do have another example for you. So I know it's kind of a long video, but again, you don't have to watch it. You can pause it, do something else, and come back for later if you want more examples. But I wanted to give you some more examples. And this one's a little tricky. I'm actually a little curious about this myself. I don't like doing these beforehand because I like to show my actual logic. I don't like to play act. I like to show the actual logic of how I approach these problems. So let's do this one. Prove that the number of steps required by a binary search on a binary search tree of size n is at most log base 2 of n plus 1. Let's unpack that for a little bit. There's a lot of terms going on here. Remember how binary search trees work. The whole idea about a binary search tree, right, is if you have the root as some, let's just do, I think a lot of the examples we did in this class were alphabetical. So if you have some name over here, then everything to the left should be before that name alphabetically. Everything to the right should be after that name alphabetically. And then over here, everything to the left of that one should be before alphabetically, and everything to the right should be after alphabetically, but still before the first thing. Right? Basically, binary search trees was every left subtree should always be before the root, and every right subtree should always be after the root, and that's true for every node and every subtree of that node. Okay, so remember, one of the cool things about binary search trees is that we can go through them very fast because we just compare every node and say, okay, what are we looking for? Oh, it's before this, so we must go to the left. Oh, it's after this, we must go to the right. Oh, it's after this, we must go to the right again. Okay, so that's what it is, and we're going to say that if there's n nodes, the number of steps required is going to be at most log n plus 1. Now, this logarithm may seem a little weird. Let's actually prove something else first. And I'm going to prove something much simpler first, and then we'll talk about, I don't think we're actually going to do it, we're going to talk about how we could use that to get here. So let's prove something else first. Let's prove that for a binary search tree of depth n, the max steps, sorry, not depth, height. I always use the wrong word there. Of height n, the max steps is n plus 1. And then we're going to talk about how we can use that result to say other things. Now, this is a much easier thing to prove, right? Because of a binary search tree, right? I feel like you almost don't even need to prove this. I feel like this is pretty obvious, but a lot of obvious things still need proving because there are obvious things that we think are obvious that are actually wrong. Case in point, the textbook author saying that everyone of legal drinking age can vote, which is not true in the United States while I'm recording this video. Okay, so what is our predicate going to be? Let P of n be the proposition, this is true, for a tree of height n. Then our base case is going to be n equals 0. All right. So if you have a binary search tree of height 0, what does that binary search tree look like? It just looks like one node. How many steps is it going to take you to find that node? Just one. All you have to do is look at the node. All right. Just takes one step. And we wanted to show that the max steps is n plus 1. Yep, that is n plus 1 because n was 0. That's it. That's it for the base case. Now the induction case, or base step. And the induction step is going to be, does it being true for height n imply it's true for height n plus 1? So again, we're going to do our induction hypothesis. We're going to assume it's true for height n, that the max steps for a binary search tree of height n is n plus 1. We want to show the max steps for a binary search tree of height n plus 1, the max steps is n plus 2. All right, and I'm kind of starting to draw behind my head. So let's take this to a new page. Can we do this? Can we say that if blue, then green? Well, yeah, of course we can, right? Because if we do have a binary search tree, right, we can kind of use the same picture that we did before, right? If we have a binary search tree of size n, then essentially we can do all the steps to get to this level in n plus 1 steps. Well, there's only one more level to go. It's only going to take one more step. Okay? So yeah, it's only going to take one more step. Here we're going to do this more logically and say, yes, you know, we can get to the second to the bottom. I don't know, that's supposed to be the word second. Second to bottom in n plus 1 because of our induction hypothesis. Then it's just one more step. Maximum. All right, we can, and again, this is a search algorithm, so if we really want to be more precise, we wouldn't say we can get to the second to bottom level, right? We'd say we can search anything up to there. In fact, really should kind of say that, is that we can search anything, right, in the top n levels in at most n plus 1 steps. Well, the worst case scenario is if we're in that last level, and that'll just take one more step. So that's n plus 1 is n plus 2. Yeah, so we've shown now this green step. We've proven the inductive step. And so by this logic, right, by induction, we've shown this. By induction, blah, blah, blah. We could say P of n for all n greater than or equal to 0. So that's the induction part that I wanted to show. And then I do want to just kind of show how this is similar, how we could then take this induction step to go over here. And it has to do with how many, right? How many nodes are in a tree of height n. And this is when we really have to specify a couple of things and we get into some more complicated assumptions, which is why we're not going to fully prove this, but I want to talk through this, right? We talked about balancedness of these trees, and we would need to rebalance it because, of course, if we had a binary search tree that was one of those silly situations, right, then we might want to rearrange things, but I'm pretty sure we would use some kind of logic along the lines of, yeah, okay, we can make this, if we rebalance this binary search tree using one of the methods that we talked about in this class for rebalancing it, then essentially we can use the fact that we're going to have these trees kind of if like at a certain height, it's going to be on the order of 2 to the k nodes. And then here it's talking about how many nodes. And then so this is kind of like the height, and we switch that. And if something's 2 to the k, and if we solve for k, we're going to get a log base 2. And that's kind of how that's going to translate and how we could kind of use this logic to get there. Again, not going to fully prove this, but kind of start and talk about what are the things that are involved. And then I'd be curious to see if anyone wanted to prove this as well. I think there might be a way to more directly use induction on this. But I'm not quite sure. I do think you need some kind of assumption of rebalancing. Curious to see what people think about that, though. But that's one practice for induction. And at the very least, this blue part is good induction practice, and that's more straightforward. But as you can see, sometimes proofs can get into some pretty cool and tricky stuff. And that's one of the really important things for, like, anytime you're proving a theorem or really trying to prove something new, is having like peer review and stuff like that. Because even if we think that we've proven something, it's useful to have other people examine kind of our assumptions. Anyway, it's cool. It's fun. Hope you enjoy induction and have a good one.